The paper is Learning Fast and Slow Towards LLMs that Adapt Continually. And the core problem it tackles is this. Adapting large language models through standard reinforcement learning forces all task-specific information into the model's parameters.
Right, the slow weights.
Exactly, the slow weights. And doing this causes catastrophic forgetting. It creates a massive loss of plasticity, meaning the model just loses its ability to learn future tasks.
It's a huge bottleneck.
Yeah. So the authors introduce a solution called fast-slow training, or FST. It co-evolves the model's parameters with a population of optimized textual prompts, which act as the fast weights.
And the results are actually pretty wild.
They are striking. FST is up to 3 times more sample efficient than RL alone. It consistently reaches a higher performance ceiling, and it results in up to 70% less KL divergence from the base model.
Wow.
Because the parameters drift less, the model preserves its plasticity. It can continually learn new tasks on the fly in scenarios where parameter-only RL just completely stalls.
It fundamentally re-engineers how a neural network distributes the burden of learning a new task.
Yeah, and if you're an ML engineer or a researcher sitting in front of your terminal right now, that summary probably sounds like the holy grail.
Oh, absolutely.
Because we all know the absolute pain of this process. You spend a massive compute budget to fine-tune a model on a new domain, say like a highly specific coding task or legal reasoning.
Right.
And suddenly you realize it has completely forgotten how to do basic logic.
Yeah, the classic catastrophic forgetting.
Or worse, you try to update it a week later with the second task, and the model just refuses to learn. It stalls out completely.
It's so frustrating.
It really is. Yeah. So to understand why fast-slow training manages to break this curse, we have to look at the fundamental bottleneck of current post-training methods.
Right, and that bottleneck really comes down to capacity and persistence. Whether you're using supervised fine-tuning, PPO, GRPO, or RL with verifiable rewards, the architecture relies entirely on parameter updates.
The mathematical weights.
Exactly, Seda. The weights of the neural network are forced to do all the heavy lifting. Think about what we're actually asking those parameters to memorize during a standard post-training run.
That's a lot.
It is. They have to hold on to every broadly reusable reasoning skill while simultaneously etching in every temporary task-specific heuristic.
Right.
And every transient lesson learned from just a single successful training rollout. It all gets pushed into that exact same persistent set of weights.
Which it makes me think of using a single whiteboard.
Oh, I like that.
Yeah, imagine you have one whiteboard in your office and you use a permanent marker to write down the fundamental laws of physics.
Okay.
That represents the model's general reasoning ability, its base understanding of the world. But then you use that exact same whiteboard and the exact same permanent marker to scribble down today's grocery list.
Right, the task-specific stuff.
Exactly. The highly temporary heuristics you need just for today's benchmark. Eventually, your whiteboard gets so overwritten with grocery lists that you can no longer read the laws of physics underneath.
You literally can't see the base reasoning anymore.
Yeah. And worse, you have no blank space left to write down tomorrow's tasks.
Well, I'd even push that analogy a bit further because mathematically, it isn't just about running out of space.
Oh.
Yeah, it's about active destruction.
Huh.
When you improve the in-domain reward using standard RL, the gradients literally force the policy distribution away from its base behavior.
Wow. Okay.
You're deliberately overwriting the physics to make more room for the groceries. And the paper points to the specific fallout from this mechanism.
Which is what exactly?
Well, you see a severe reduction in output entropy, meaning the model's response has become extremely narrow and rigid.
Right.
You see degraded out-of-distribution generalization. And most critically, you see plasticity loss. The parameters become so overly specialized.
They just get stuck in a local minimum.
Exactly. They become so entrenched in that minimum for the current task that they physically lose responsiveness to gradient signals from any new tasks you try to introduce later.
Which brings us to this whole idea of fast and slow weights. If the parameters are the slow weights, the permanent marker on the whiteboard, we need a fast channel.
Yeah, and stepping back for a second, this isn't a completely novel philosophy,
Really?
Yeah, the authors are drawing on some very deep historical and biological roots here. In neuroscience, we talk about complementary learning systems in the brain.
Oh, like the hippocampus.
Exactly. The hippocampus handles rapid temporary memory, while the neocortex handles slow, structured integration. It maps really closely to Daniel Kahneman's System 1 and System 2 thinking.
Oh, that makes a lot of sense.
Right. And in neural network history, Geoffrey Hinton actually published a paper exploring a fast and slow weight distinction way back in 1987.
1987, wow.
Yeah. So the theoretical goal has always been to separate temporary, rapid adaptations from persistent, broadly useful behaviors. What makes this paper so compelling is how brilliantly they engineered an instantiation of that concept for modern LLMs.
So let's unpack how they actually engineered that instantiation. Offloading the grocery list from the parametric weights is where the technical architecture gets really interesting.
It does.
Fast-slow training operates using two interleaved loops. Let's start with the slow loop, which is essentially what you, the listener, are already used to doing.
Right, standard RL.
Yeah, it updates the parameters, theta, using scalar rewards via a standard RL algorithm. In this specific paper, they use CISPO or GRPO. So the model gets a math problem right, it receives a scalar reward of 1.0.
And if it gets it wrong, a 0.0.
Exactly. It hallucinates or messes up, it gets a flat 0.
But the limitation of that slow loop is that it only ever sees a binary or scalar reward.
Yeah.
It knows that it failed, but not necessarily why it failed.
Right.
The fast loop, on the other hand, operates completely differently. It updates the textual context, the fast weights, denoted mathematically as phi, using a process the authors call GEPA.
Generative Evolutionary Prompt Adaptation. And here is where the divergence happens. The fast loop does not just look at a 0.0 or a 1.0. It consumes incredibly rich natural language textual feedback.
Which is huge.
It really is. It looks at the model's intermediate scratchpad thoughts, its tool calls, and its exact execution errors.
So it gets the full picture.
Yeah.
Yep.
If the slow loops model fails because of a zero division error on line 5 of a generated Python script, the RL algorithm just passes back a flat 0 reward.
Right, which isn't very helpful.
No. But the fast loop actually reads the string zero division error division by 0 on line 5, and it can immediately use an LLM acting as an optimizer to reflect on that specific text and rewrite the prompt.
To prevent that exact error in the next pass.
Exactly.
And the architecture of GPA is highly sophisticated. They aren't just optimizing one single golden prompt and hoping for the best. FST maintains an entire population of prompts.
Oh, interesting.
Yeah, it actively manages a Pareto frontier of complementary textual instructions, usually K equals 8 in their experiments.
Okay, so 8 different prompts running at once.
Right. And by keeping a population, different prompts can naturally specialize in mitigating different types of errors or addressing different subsets of the training data.
That's clever.
It is.
Right.
The optimizer iteratively mutates these prompts, evaluates them on mini batches, and keeps the ones that yield the highest reward, constantly refreshing this fast weight channel.
Okay, I have to push back here for a second.
Sure.
As someone who follows the post-training space closely, and we talk about this a lot on AI paper podcasts, we've seen prompt optimization before.
Oh, absolutely.
There's DSPy, there's OPRO. There are a dozen frameworks for having an LLM optimize its own instructions. So what is actually fundamentally new about FST? Because it sounds like we are just doing prompt engineering on top of reinforcement learning.
It's a fair question. The distinction really lies in the timing and the integration.
How so?
Well, previous methods like DSPy treat prompt optimization and model training as completely sequential, isolated phases.
Right, you do one then the other.
Yeah, you might train your policy with RL for a week, freeze the final checkpoint, and then run prompt optimization over it. Or vice versa, you figure out the best prompt and then do some fine-tuning.
Okay, so how is FST different?
Fast-slow training co-evolves them simultaneously in a shared training loop. It runs a cycle of GPA to optimize the population of prompts, and then it holds those prompts fixed for a short window, say 6 steps of RL.
Ah, I see.
During those 6 parameter update steps, the newly evolved prompts are actively mixed within the rollout groups.
So the textual context and the neural policy are physically sharing the adaptation burden in real time, step by step.
Exactly. The fast textual weights rapidly incorporate the immediate lessons from the rollouts, providing a temporary scaffold that steers the model toward better reasoning immediately.
Wow.
Then, the slow parametric weights are updated under the influence of this newly evolved, highly effective context.
So the gradient updates become much higher quality because the model is already being guided to the correct answer by the fast weights.
Precisely. The performance gains are distributed across both channels, instead of forcing the parameters to absorb the entire shock of a new task from scratch.
That makes perfect sense theoretically, but what does this coevolution actually look like when you run it? Like, how does it change the trajectory of a training run?
It changes it completely.
Let's bring in the StarGraph search task they tested, because I think it perfectly illustrates how FST escapes a massive trap that standard RL constantly falls into.
Yeah, the StarGraph task is a great example. It's a synthetic reasoning problem designed specifically to be a worst-case scenario for reinforcement learning.
Right.
The model is given a graph and tasked with finding a specific path between a start node and an end node. Crucially, it's a hard exploration problem. The source node might have 25 decoy branches leading to dead ends and only one correct path.
And in a standard RL setup, if your model takes a wrong branch, it gets a reward of 0.0. The gradients are entirely flat. The paper shows that standard parameter-only RL just sits at near zero reward for roughly 300 training steps on this task. It is guessing blindly, getting zeros, and learning absolutely nothing because there is no positive signal.
But the model trained with FST escapes this zero reward regime by step 50. It solves the exploration problem an order of magnitude faster.
And it does that because of the rich text feedback. The GPA fast weights aren't waiting for a gradient update.
Right.
They read the text of the rollout, see exactly which path hit a dead end, and instantly inject a semantic correction into the prompt for the very next rollout.
It's immediate.
Yeah, the fast channel completely bypasses the latency of gradient descent. It extracts the structural rules of the maze from just a handful of failed rollouts and immediately provides a textual scaffold.
And that scaffold guides the model down the right path, which finally gives the slow parametric weights the positive scalar reward signal they need to actually start learning.
That's amazing. And that synthetic example translates directly to massive data efficiency gains on realistic domains too, right? Oh, absolutely. When they evaluated FST across code output prediction with the Code I/O dataset, advanced mathematics with Polaris, and multi-hop fact verification with HoverHard, FST reached the peak performance of standard RL using 1.4 to 3 times fewer training samples.
That is massive. I mean, if you're managing a compute cluster, reaching your target performance in a third of the steps is an incredible win.
It's huge.
But, as I was reading this, a massive red flag went up for me regarding the infrastructure.
Let me guess, the wall clock time.
Yes. When I hear coevolution and LLM-based prompt optimization in the training loop, I immediately think, wow, generating all those extra rollouts to judge the prompts is going to absolutely destroy my training time.
Sounds incredibly expensive.
Yeah, how does this not double the length of a training run?
That is where the authors introduced a really clever mechanism they call rollout reuse. It bridges the gap between the fast loop and the slow loop efficiently.
How's that work? Well, during the GPA phase, the system obviously has to generate a large batch of evaluation trajectories just to figure out which mucated prompts in the K=8 population actually yield the highest reward.
Right.
In a naive implementation, you would just throw all those trajectories away once you pick the best prompts.
But FST doesn't throw them away. It takes those exact rollouts generated during the prompt evaluation phase and dumps them directly into the RL buffer for the next step.
Right. And mathematically, this is perfectly valid for on-policy RL.
Really?
Yeah, because the prompts chosen by the GPA phase are the exact same prompts the RL phase is about to use, and the underlying policy parameters haven't been updated yet.
Oh, so those trajectories are perfectly on policy.
Exactly. They're completely valid for computing the policy gradient.
So you get the prompt optimization almost for free. The efficiency gains there are wild.
They really are. On the HoverHard task, reusing those rollouts drops the wall clock time per RL step from 66 seconds down to 47 seconds.
That's nearly a 30% speed up.
Yep, and they demonstrated that it comes with zero loss in final accuracy. Roughly 20% of the trajectories used to update the parameters end up being served straight from this GPA cache.
Wow. And with that efficiency, FST doesn't just learn faster, it converges to a significantly higher ceiling altogether. On the Code I/O benchmark, FST hits an asymptote 4.4 percentage points higher than standard RL.
And on HoverHard, it is 7.7 points higher.
Which naturally leads to the next question, right? If the fast weights are so good at finding these high ceiling strategies, could we just run GPA to figure out the best prompts and then forcefully distill that knowledge directly into the parameters without bothering with the complex RL coevolution?
Ah, the distillation approach. The authors anticipated that exact question and explicitly tested it with an experiment called FST Distill.
What did they do?
They took the prompt-optimized model and tried to use an on-policy reverse-scale distillation loss to teach the base model.
Yeah.
Essentially, they tried to make the base parameters chase the outputs of the fast weights.
And it fails.
Yeah, it completely fails. Distillation alone plateaus well below the performance ceiling of FST.
Why is that?
Observation 2 in the paper explicitly details why this happens. Both channels, the fast textual weights and the slow parametric weights, must be optimized against the environmental reward jointly. The fast channel alone isn't enough to capture the full complexity of the task, and trying to blindly distill the text back into the parameters strips away the dynamic interaction between the two.
So the parameters still need to experience the friction of the environment through their own gradient updates.
Exactly. You can't just hand them the answer key.
Okay, so we've solved the exploration trap, we've skyrocketed data efficiency, and we've hit higher performance ceilings without ruining wall clock time. But let's bring it back to the very first problem we discussed, catastrophic forgetting and plasticity loss. We know FST performs well on a target task, but how does this dual-channel approach actually impact the long-term health of the base model?
The most direct way to measure this is by looking at KL divergence,
which quantifies how far the post-trained policy distribution has drifted from the original base model's distribution.
Right. When you compare FST models and standard RL models at matched reward levels, the FST models sit way to the left on the KL divergence graph.
Meaning the parameters simply do not drift as far from their original state.
Exactly. Because the fast weights are absorbing the shock of the new task. The parameters don't have to contort themselves to memorize the grocery list, so they stay closer to the fundamental physics.
That's a beautiful way to put it.
There is a critical nuance there, though.
Oh.
Yeah. They did find one exception on the Math Polaris task, where the KL divergence between FST and RL was practically identical.
Why was that?
When they dug into why, they found it came down to the base model used for that specific task. They used a weaker, early-stage, supervised fine-tuned model that simply couldn't follow complex instructions very well.
So if the base model isn't strong enough to actually comprehend the highly optimized prompts generated by the fast channel, the whole architecture breaks down.
Right. The fast weights try to provide a scaffold, the model ignores it, and the slow weights are forced to carry the entire burden of learning the task anyway.
That makes total sense. So FST heavily relies on a strong, instruction-tuned base model. The model has to be capable of being steered by text.
Exactly. But assuming you have a capable base model, the preservation of plasticity is remarkable. To empirically prove this, they ran a plasticity probe.
Let's talk about that.
So phase 1. Train the base model on the math dataset until convergence. Phase 2. Take that fully trained checkpoint, freeze everything, and try to train it from scratch on a completely different domain, the hover verification task.
And the results of that probe are staggering. The model initialized with standard RL collapses to 0% learnability on hover.
It flatlines entirely.
Yeah. It is so overfitted to solving math problems that its gradients are dead. It has completely forgotten how to learn a new task.
But the model that was initialized with FST in phase 1 manages to hit 16.7% accuracy on hover in phase 2.
That practically matches a fresh, untouched base model's capacity to learn.
Yeah, it's incredible. And they push this concept to its absolute limit with a continual learning stress test. This is where the real-world application really shines.
What did they do?
They ran a single, uninterrupted training pass of 600 steps. But every 200 steps, they abruptly swapped the data set. They started with 200 steps of hover, immediately shifted to 200 steps of code I/O, and then finished with 200 steps of physics.
A total nightmare scenario for standard reinforcement learning.
Complete nightmare. When the objective suddenly switches from hover to code I/O at step 200, the standard RL model stalls terribly.
Because it's too rigid, its weights are pointing the wrong direction.
Right. Over its entire 200-step budget on code I/O, it only manages a measly 2.5 percentage point gain.
Yikes.
But FST, on the other hand, pivots instantly. It climbs 19.6 points on code I/O in less than half the time.
Wow.
It adapts to the changing objectives dynamically because the fast weights rewrite themselves instantly to scaffold the new domain, giving the slow weights the time they need to catch up.
Hearing how much heavy lifting these fast weights are doing leads me to what I think is the most fascinating question in the entire paper.
What's that?
What do these GPA-evolved prompts actually look like at the end of training? Because I think most of us listening have a very specific idea of what a good prompt looks like, you know?
Sure.
When we sit down to write a system prompt, we write these hyper-eloquent positive affirmations. You are an expert software engineer. Please think step by step and write clean, modular code.
That is exactly what you might expect an LLM to generate when asked to optimize a prompt.
Right. But the reality observed in the experiments is entirely counterintuitive.
Totally. If you look at the raw text of the evolved fast weights in the paper's appendix, they do not look like generic positive system prompts at all.
What do they look like?
They evolve into highly specific, almost aggressive checklists of don'ts.
Checklists of don'ts. When I read that, I was genuinely surprised.
It is fascinating model psychology. GEPA rarely wastes tokens rewriting the original seed prompt. Instead, it appends strict negative constraints based on the actual granular mistakes the policy made during the failed rollouts.
That's so interesting.
Yeah. For instance, on the Code.io task, the evolve prompt explicitly includes the line, never estimate, intuit, or placeholder any result.
Because it observed the model being lazy.
Exactly. It saw the model inventing placeholder numbers because the computation was getting too long, and it hard-coded a rule to stop that exact behavior.
It is so hyper-specific. I saw on the hover hard verification task where the model has to navigate Wikipedia pages, the prompt literally evolved to say, do not skip pages with parenthetical disambiguators.
Right.
Because the model was constantly failing when a band and a movie shared the same name, and it kept skipping the page that had the parentheses in the title.
It acts less like a broad instruction manual and more like a hyper-personalized list of bug fixes for the model's own brain.
I love that.
It reads like an exasperated teacher saying, look, I know your parameters always fail to carry the 1 in this specific edge case, so do not forget to carry the 1.
But why is it so heavily skewed toward negative constraints? Why does the fast channel default to telling the model what not to do?
It comes down to the inherent division of labor. Neural network parameters, the slow weights, are exceptional at generalizing positive, broad reasoning patterns.
They are very good at learning how to write code or how to search a database.
Exactly. But what parameters are terrible at is remembering highly isolated categorical exceptions.
Oh, I see.
Forcing the parameters to learn never skip parenthetical disambiguators requires contorting the weight space, which destroys generalization.
Right.
By offloading those isolated negative constraints into the text channel, the parameters don't have to memorize the edge cases. They can just focus purely on general reasoning, guided by the guardrails of the text.
That makes perfect sense. So, synthesizing everything we've covered today, we are really looking at a fundamental paradigm shift away from monolithic parameter updates.
Without a doubt.
The core takeaway for anyone listening who is building or fine-tuning models is that effective post-training shouldn't just forcefully shove all task adaptation into the slow weights.
Right.
By utilizing textual channels to share the adaptation burden alongside parameter channels, we get models that train faster, reach higher performance ceilings, and most importantly, stay plastic and adaptable for whatever task comes next.
It's a systemic acknowledgement that not all knowledge is created equal, and therefore not all knowledge belongs in the weights.
Which leaves us with a really provocative thought to mull over.
Ooh.
Yeah, if these fast textual weights naturally evolve into highly specific checklists of don'ts that save the parameters from overfitting, could we start taking this beyond training?
What do you mean?
Could we start dynamically generating and swapping these negative constraint checklists at inference time based on the user-specific query?
Oh, wow.
Imagine a future where continual, lifelong learning doesn't involve gradient updates at all. Your deployed model is entirely parameter frozen, acting purely as a general reasoning engine.
But it relies on a real-time retrieval system.
Exactly. It pulls the exact fast weight bug fix checklist needed for whatever obscure task you just prompted it with. Are we moving toward a world where the model's weights are just the engine block and auto-generated prompts act as the steering wheel for every single distinct task we ever encounter?
That is a wild thought.
Something for you all to think about.